Okay, we're going to look at a practice problem using Coulomb's law. And this problem reads, two 1.2 kilogram masses are 0.7 meters apart on top of a table. So I'll just draw that in there. So we have mass 1, mass 2, they're 0.7 meters apart, and the mass of 1 equals the mass of 2, which equals 1.2 kilograms. All right. The table's frictionless, and each object has a charge of 10 microcoulombs. So the charge on Q1 equals the charge on 2Q, which equals positive 10 microcoulombs. What's the electric force on each mass? And if they're released from rest and allowed to move, what will be the acceleration of each mass? So part A is what is the electric force, and part B is what is the acceleration. This is for each. All right, so let's use Coulomb's law to determine what that electric force is. So we know that object 1 and object 2 are interacting with each other, and so they're exerting a force on each other, and that's an electric force defined by Coulomb's law, which is K Q1 Q2 over R squared. So if I'm interested in that electric force, I have 8.99 times 10 to the 9th times 10 times 10 to the minus 6, 10 microcoulombs, times another 10 microcoulombs, all divided by 0.7 squared. So using Coulomb's law, I find that this force is a positive 1.835 newtons. So the electric force on both particles is a positive 1.835 newtons. Now I want to determine what's the acceleration. So this is part A. All right, well, these two objects are acting on a horizontal surface. So we're only going to worry about the horizontal forces. And the electric force is the only horizontal force acting on them. So that's the only one we need to worry about. So the sum of the forces, the net force acting on them, is just by the electrical force. So the net force, let's go with particle 1, is equal to the mass times the acceleration of particle 1. We know that's our Newton's second law. And the only force acting on is the electric force on particle 1. But now that we've shifted into motion, we need to recognize this is now motion direction. So what is the direction of the acceleration on particle 1? Because we need to understand the direction of the force on particle 1. Well, if I look at particle 1, the electric force tells me that it's positive. So it tells me that it's repulsive. So then I have to go to my picture. Well, repulsion in this case means that force 1 is in that direction. The force on object 1 is to the left, and the force on object 2 is to the right. So the motion direction of the electric force on object 1 is negative. We have to pay attention to that. All right, so I need to calculate the acceleration of object 1. I know that I have the acceleration of object 1 is going to equal the electric force, which is negative. I'm being explicit about putting in that negative number, over the mass. So I have negative 1.835 over the mass of 1.2 kilograms, and that acceleration is a negative 1.5 meters per second squared. So the acceleration of object 1 is negative 1.5 meters per second squared. I've been explicit about my direction of that force using my picture and recognizing that I have a repulsion. What about object 2? Well, they're the same mass. So they're experiencing the same force. They have the same mass. They have to have the same acceleration. They experience the same force, Newton's third law pair. In this case, they have the same mass. So I can deduce with reasoning that the acceleration on object 2 is equal to positive 1.5 meters per second squared. Why is it positive? Well, the change in motion is to the right. The force is to the right. So positive 1.5 meters per second squared. All right, so using Coulomb's law to get the magnitude of that force, recognizing the direction that the positive or negative that comes out of Coulomb's law tells me whether I'm repulsive or attractive. In our case, this was a positive, so it was repelling. Repelling tells me that the force acting on object 1 has to be negative in direction, so we'll have a negative acceleration. The force acting on object 2 has to be positive in direction, and we'll have a positive acceleration. And of course, if I had different masses, I would follow the same process for object number 2. But since we have the same masses, we can conclude that the accelerations must also be the same, but opposite direction. All right, good job.